Logarithms are related to exponents, and remember that we've learned several important properties of exponents. And it turns out, because of the relationship, every property of exponents actually has a corresponding property for logarithms. In this video, we're going to figure out what some of those properties are and how we can use them when we're working with logarithms. So for example, remember this property of exponents. If I have two values added together in the exponent, I can actually split that up and change it into a product of two factors, each of which has just one of the two terms from the exponent. So we're going to use that to answer the following kind of question. Suppose that we already know the logarithm of a and the logarithm of b. And we want to figure out what's the logarithm of a times b. Now, it's not what you might first guess. It turns out you do not just multiply these two values together to get this one. That's wrong. You have to do something different, although it's not much harder. In fact, it's in some sense easier. Let's see how it works. We're going to deduce the right rule first, and once we have the rule, we'll be able to use it in the future to answer this sort of question very quickly. So first of all, what does this mean? Log base 2 of a means the power of 2 that gives you a. So if we make this a power of 2, the result should be a. That's where this equation is coming from. Similarly, log base 2 of b, that's the power of 2 that gives you b. So that's where this equation is coming from. You can think of this whole thing as just the exponential form of what this means. So now that we've got ways of writing a and b in terms of their logarithms, what we can do, since I'm interested in what's going on with a times b, is plug these in. So for example, I can take this quantity and plug it in for a, and then this quantity, plug it in for b. Now I've got two quantities multiplied together. Each of them is an exponential expression with the same base. Well, that brings me back to this property. Here I have two exponential expressions multiplied together with the same base, and this property tells me I can combine them by adding the exponents. So if we do that, we get these two values added together in a single exponent, and that exponent is the power of 2 I need to get a times b. So that exponent is the logarithm base 2 of a times b. It's the power of 2 that gives me a times b. So notice, since I want the logarithm of a times b, I don't just multiply the two logarithms together. It turns out the right thing to do is to add them together. So this is a general rule we can use now. If I want the logarithm of a product, I can add the two separate logarithms together. Let's use that rule to answer this question. I want to simplify this expression into a single logarithm instead of writing three logarithms. Now ln here, remember ln of a number is really just log base e of that number. Okay, so I'm using this property where my b is Euler's number. So let's see what we can do. First of all, I can combine these two expressions together using this property. I have two logarithms that are added together, and I can combine them if I just multiply what's inside. This x times this x is giving me x times x, which is really the same thing as x squared. Now I've got two logarithms added together, just like this, and I can combine those by multiplying these arguments together. 2 and x squared multiplied together just gives me 2x squared. So this is a single logarithmic expression. One logarithm to represent the same value that could also be represented by adding these three logarithms together. A similar related rule for logarithms is this one. So just like multiplication inside becomes addition of the logarithms, division inside becomes subtraction of the logarithms. Let's use that to combine this difference. These are both common logarithms, right? So they're both log base 10, but we're not writing the tens because that's our shorthand notation if we leave it off. So I want to combine these into a single expression. So since I have a difference here, I can combine them by dividing the arguments. So to combine them, I divide this quantity by this quantity, giving me this fraction. Now it turns out you can simplify that some more because you can cancel factors of x that appear both in the numerator and the denominator. X squared over x, you can cancel out an x, and now you have x to the 1. Similarly, you can cancel factors of y. Y in the numerator cancels with one of the y's in the denominator, leaving just y to the 2. So this is really going to simplify all the way down to the common logarithm of 5x over y squared. We can also split up an expression using the property for multiplication inside. So take a look at x cubed. X cubed is really the same thing as x times x times x. And so we're multiplying those quantities together inside of the logarithm. And our first property tells us we can split that up into a sum of each logarithm taken separately. Now each of those quantities are the same thing. Log of x, log of x, log of x all represent the same thing. So we can combine like terms and write that as 3 times the log of x. And notice what's happened here. We started with log of x cubed. We ended up with 3 times log of x. And a nice shortcut for thinking about how this operation results in this expression is to imagine that we're just taking this exponent and moving it out front, putting it right here. That's exactly how we're going to think of this. So the general rule works for any base, and you can always think of it this way as if I have a quantity I'm taking a logarithm of that's an exponential expression, x raised to a power, then I can just take that exponent and bring it out front, like we see here. Now, the way we've deduced this rule assumed that the exponent was a whole number, but this property works even when it's not a whole number, even when it's not a positive number. We can still bring this exponent out like this. We'll use this rule a lot when we start solving equations involving exponential functions. Here's an example of how we could use this property. If I want to write this as a single logarithm, 3 times log base 2 of x plus 4 times log base 2 of y, then the first thing I can do is use this rule, but actually I'm going to use it in the opposite direction that we just deduced it. I'm going to take this coefficient out front move it inside, and when I move it inside, it becomes an exponent. Same with this coefficient. When I move it inside, it becomes an exponent on the y. So I get log of x cubed plus log of y to the fourth. And then I can simplify some more. I'm trying to write everything as a single logarithm. I have a sum of logarithms, and another one of our properties tells me that I can combine that into a single logarithm by just multiplying these two arguments, x cubed and y to the fourth. So that gives me log base 2 of x cubed times y to the fourth. Let's use the same ideas in the other direction. This time I want to write the natural logarithm of 2x to the fourth so that there aren't any exponents in my expression. So I can start with the natural logarithm, and notice the argument 2x to the fourth, that's really 2 times x to the fourth. There's a multiplication going on between these, and I can split that up into a sum. Once I've split it up like this 4 is an exponent of this x, and so the property we just learned that allows me to bring the exponent out front allows me to rewrite the expression this way, natural log of 2 plus 4 times natural log of x, and notice that there aren't any exponents left when it's written this way. Now, a common mistake when you see this kind of question would have been to try to move this 4 out front right away, which would have given you 4 times natural log of 2x. But this is not correct. That does not give you the right answer. And the reason is you cannot use this rule yet because the 4 is not an exponent of the whole thing. I cannot bring it out front until it's an exponent of the whole thing inside. It's an exponent of the x, but not an exponent of the 2. That's why I have to split the 2 apart first using a different property before I can bring the exponent out. Finally, we're going to look at a property that tells us how to evaluate other bases for logarithms. So for example, suppose I want log base 3 of 20, and I want to come up with an approximation for that on the calculator. Now, log base 10 is easy, there's a button for that. Log base e is easy, there's a button for that. But what about log base 3? There's no button for that. So, here's how we can proceed. First of all, let's just use the symbol x to represent the number we're trying to evaluate, log base 3 of 20. Because writing it this way will let me express this relationship in an exponential form. Log base 3 of 20 means the power of 3 that gives me 20. X is the power of 3 that gives me 20. Now, I know how to work with common logarithms, so let's do that. Let's take a common logarithm of both sides, log base 10, because we have a button for that on our calculator, so I'll be able to take advantage of that later on. Now, the reason to use a logarithm here is because I can use that property of logarithms that lets me bring the exponent out front. This is going to be a really useful tool when we solve more equations involving logarithms. Equations like this one, but that are maybe even more complicated. So, by taking the logarithm, now I can bring the exponent out front. And now this is just multiplication. This is x times log of 3. Log of 3 is a number, so I can isolate x if I divide both sides by log of 3. Now, x is what we were trying to compute. It's log base 3 of 20. So log base 3 of 20 is common log of 20 divided by common log of 3. And that's something that I could plug into the calculator. So the ideas in the previous screen show us this rule. To get a logarithm with any base, I can take a logarithm base 10, a common logarithm, and then divide by the common logarithm of the base that I really want. So for example, if I want log base 4 of 19, go into a calculator, I can type log of 19 and divide that by log of 4, giving me approximately 2.12, which is the right answer.